to show you how the canceling out or the destructive interference takes place. In this lesson, we are going to talk about the chapter on superposition, and we are going to see what is destructive interference. Let's say this is a rope and I'm moving the rope in the downwards direction and then back upwards. That way, a trough is going to get created and the trough appears to move towards the right. And let's say on the other side of the string, I move the source in the vertically upwards and downwards direction. That way I will end up creating a crest. So this is a crest and this is a trough. Okay, I'm just creating half a wavelength on both sides. That means a trough or a crest, which means that it's half a wavelength. So when they travel, the crest will travel towards the left and the trough will travel towards the right. Let's say P is a point on the string, and when a crest reaches this point, the crest is trying to move the point P in the upwards direction. Because we remember when a crest moves, the direction in which it is moving, the particles on that side of the crest, they are all moving in the upwards direction. So the crest, when it is trying to move through P, it will first displace the P in the upwards direction. And when trough reaches the point P on this side, the trough tries to pull the point P in the downwards direction. So at the same instance, when crest and trough meet at a point P, what happens? The crest tries to move the P in the upwards direction, and the trough tries to move the point P in the downwards direction. So if I say both of them, they have same amplitude. Let's say this is A and this is A as well. If both of them have same amplitude, that means at point P, both their effects are going to get cancelled out. Thus, when the crest tries to move through P, the point P is not going to move anywhere at all. It's not going to get displaced upwards. It's not going to get displaced downwards, because at the same instance, one crest is trying to pull it upwards and the other trough is trying to pull it downwards. So the effects get cancelled out. So such cancellation of the effects of waves is called destructive interference. We take a little break and see if you understood that.
I got it.
Okay, that's great. Now, if you want to see the constructive interference for trough, I will show you that as well. Constructive interference of trough. Okay. Originally, I should have shown this to you where I showed you the addition of crests, but I thought it was kind of a given, but I will still show it to you on a separate diagram here. Let's say this is a source and this is also a source. I'm moving this source downwards and then back upwards. That way I will create a trough over here. And if this source is also moved vertically downwards and then back towards the mean position, we will end up creating a crest, as creating a trough as well. The wave always moves away from the source. So the source on the left will create the trough which will travel towards the right, and the source on the right will create a trough that will travel towards the left. So let's say P is a point. When the leftwards trough reaches the point P, it tries to pull the point P in the downwards direction first. And when the trough coming from the right reaches the point P, it also tries to pull the point P in the downwards direction. Because both of them are trying to pull the P in the same direction, so as a result of them, the P is going to get displaced to a displacement that will be equal to both their amplitudes added together. Both the waves are trying to pull the point P in the same direction. That is why their effects will get added. I often give an example that imagine two people have to apply a force on a box. If both of them apply the force in the same direction, the net force gets added. But if both of them are applying a force in the opposite direction, their effects get cancelled out. This was constructive and this was destructive interference for you. Do you understand that?
I got it. So, sir, what about the constructive interference of an entire wave?
Okay. Do you understand the crests and troughs and troughs? I hope that
Yes.
that's not a problem.
Yeah, it's clear.
Okay, so I will show you the constructive interference of entire waves. Let's say if this is a wave and this is another wave, I am making them separately, but when they meet at a point, that means that this wave is also going to meet the first wave at such an instance where crest of one wave falls on the crest of another and trough of one wave falls on the trough of another. So when they get added together, they will result in a wave that will have an amplitude which will be the sum of their crests and troughs. Okay, so if this wave had an amplitude of 2 centimeter and this one also had an amplitude of 2 centimeter, so their crests will get added together and give you a 4 centimeter amplitude, and their troughs will get added together and will give you a 4 centimeter amplitude as well. So when complete waves interact, interfere, intersect, their crests also get influenced and their troughs also get influenced by each other. They get reinforced. But if other way around happens, that's when one crest meets the trough of another wave like this. What's going to happen when these two waves, they are going to meet together this way? One wave is trying to pull the particles upwards, the other one is trying to pull it downwards. So in such a case, when these two waves meet, they will result in a wave that's going to have a zero or a reduced amplitude. They will completely cancel each other out only if their amplitudes are equal. If this is 2 and if this is 2, they will result in a wave that has zero amplitude. But what if one of them has a larger amplitude and the other one has a smaller amplitude? Let's say this wave had an amplitude of 3 centimeter and the other wave, it had an amplitude of 2 centimeter. What happens if they both meet at a point? In such a case, one of the wave that has a larger amplitude, of course, that wave is going to win. It's going to be able to pull the particle in its own direction, but it will result in a wave that will be diminished. That means it's going to have a 1 centimeter amplitude as a result.
All right.
Okay, do you understand all of that?
Yep. Makes sense.
All right. Okay, I'll be back in a minute. Okay, sorry, I am back. Right. I will show you, I'll give you an example where destructive interference takes place in our daily life. If you know about the noise cancelling headphones, noise cancelling headphones. That's the technology working behind noise cancelling headphones. That means the noise that is reaching your ears, of course, it's going to have a compression or a rarefaction. So those headphones, they emit a wave that is 180 degree out of phase. What does that mean? 180 degree out of phase. That means exactly opposite to each other. So in such a case, the noise will get reduced because one is going to be a noise signal and the other signal is going to be generated by the noise cancelling headphones in the opposite direction to the noise. So if let's say a noise signal is trying to push the particles upwards, the system is going to produce a sound wave that's going to pull the particles in the opposite direction, hence cancelling out the effect, or not just canceling it out completely, but maybe diminishing the amplitudes or the resultant wave. That way, it will reduce the noise levels. All right. Now, the next topic that we need to discuss is going to be about two source interference. Two source interference. Now, I think we have established this so far that interference takes place only if at least two waves meet at a point. A single wave cannot interfere. Interfere means a single wave cannot have its amplitude increased or decreased. So for a two source interference, of course, I'm going to need two sources of sound or of any kind of wave, because interference takes place for any or every kind of wave. Every kind of waves can perform the interference. Okay. Now, imagine I have a big ripple tank, and that ripple tank has two vibrating sources. Let's call this S1 and let's call this to be S2. These two vibrating sources, they are attached with the same frequency generator. This is a generator that's going to vibrate these two sources. Of course, this is a ripple tank. This is going to be water over here. Okay, S1 and S2, they are going to cause vibrations in the water, because of which there will be waves traveling in all directions. So similarly, there will be waves coming from S2 as well. They will be traveling in all directions. Okay, there will be some areas where waves coming from one source will meet the waves coming from the second source. Are you with me so far?
Yes.
Okay, that's great. I am going to represent the waves by using semicircles. These semicircles are indicating the waves traveling on all the directions. Actually, these semicircles are called the semicircular wavefront. Every bold line that I have drawn here is going to indicate a crest of a wave. Okay, so these bold lines, in between them, there is a dotted line present. These dotted lines are going to show trough of transverse waves. I'm trying to keep the gap between these lines uniform, constant, because I'm drawing it freehand. So thodi si, there is this variation possible in some places. Okay, so the blue waves, they are coming from source S1. The gap between them is indicative of a wavelength. This is a wavelength, this is a wavelength, and this is a wavelength. The dotted line is indicating troughs, and the bold lines are indicating crests. Similarly, I will use a different color, a green color, for the waves coming from S2. These are the semicircular wavefronts coming from S2. I'm trying to keep the wavelength uniform and constant, because both the sources are attached to the same generator. That means S1 and S2, both of them have same wavelengths and same frequencies. The speed is also same, because both of them are producing waves which are traveling inside water. If we remember that speed of the wave is dependent on the medium. If the medium is same, the speed has to be same. So I'm going to write S1 and S2 have same frequency, wavelength, and speed. Also, the speed depends on medium. If the medium is same, the speed is same. Depends on medium. F depends on source, because both of them are producing waves from a same source. So they are going to have same frequency. And the wavelength is equals to frequency, speed over the frequency. That means if speed is same and frequency is same, that would imply that the wavelength is same as well. Okay, so in this case, the sources that I'm talking about, they have same frequency, same wavelength, and same speed. Do you see there is this small portion where the waves are intersecting? One wave from S1 and one wave from S2, they are intersecting. Okay, I'm going to show you a few points. these points, all of them, the ones that I'm indicating by yellow, they are all the points where constructive interference will take place. How do I even know that? See, if the crest of the blue wave and crest of the green wave, they are meeting at a point. See, bold lines are indicating crests. So this point here, let's call this A, let's call this point to be B, let's call this to be C, and let's call this to be D. All these points, A, B, C, and D, they are present where crest of one wave meets the crest of the other, or trough of one wave meets the trough of the other. So whenever crest and crest fall together, or troughs fall together, they create constructive interference. That means at point A, B, C, and D, the particles will be displacing to an increased or influenced amplitude. Do you understand that? B, I will show you some mathematics as well. Are you with me so far?
I am, but sir, we can't see the constructive interference.
Actually, there will be constructive interference and you will be able to detect it, but you won't be able to see it because waves will keep moving very quickly. You won't be able to see it with the naked eye, but you'll be able to detect it. If instead of water waves, they were sound waves, if I would keep a microphone over here, I would be able to see that the sound wave has an increased amplitude. I'll show this to you on a simulation as well. Don't worry. But I would have to show you some mathematics before I actually move on to the simulation. Are you with me so far?
Yes.
Okay, I'm going to show you some mathematics. Be with me. Before that, I'm going to indicate a few points where destructive interference will take place. Destructive
Yeah, another
interference,
question, sir.
yep.
Won't the destructive interference and like cancel out the constructive interference?
No, destructive interference will take place at a different position. Constructive interference will take place at a different position. Like if you can see at this point, I'm using a purple dot. There is a bold line coming from S2 and there is a dotted line coming from S1. So this will be a position where destructive interference will take place.
Yes.
Similarly, if I show you this point, let's call this X and let's call this to be Y. At Y, there is a bold line from S1. That means there will be a crest from S1 and there will be a trough from S2. So there will be a destructive interference here as well. Let's say this is a point where a bold line from S1 means crest coming from S1 and a trough from S2. They meet at point Z. So at X, Y, and Z, there will be destructive interferences taking place. Are you with me so far?
Yes, yes.
If I try to look at the particles at X, Y, and Z, I would see that those particles at this particular instant, they'll be at rest. They won't be able to move up or down, or they'll be able to move just a little. Okay. Are you with me?
Okay. Sir, doesn't superposition ruin
Ruin
the how do
the
I word this? The harmony of the wave.
well, actually,
Like how is
yes,
it still working or
yes,
moving?
yes. In some areas, there will be a point where there will be destructively interfering. So there the waves will not be able to, cause as big vibrations as needed. That is why whenever we design lecture halls, we arrange the seats in such a way that sound gets reflected and reaches from every position and interfere constructively instead of destructively. Because if destructive interference takes place for sound, there will be areas where there will be no sound heard at all, and there will be areas where there will be higher sound heard as well. So you see, there are positives because of constructive interference and there is a negative because of destructive interference. So it can actually help us increase the amplitude, or it can actually help us decrease the amplitudes as well. So we can use both of these phenomena for our advantage.
All right, all right. Sir, could you write the electoral thingy on the side? You don't have to explain it, just you could write electoral on the side so that I remember.
I couldn't catch it. What did you say?
Could you just write electoral example? right next to this diagram.
Lecture hall. Okay, lecture hall.
Yeah.
Lecture halls or amphitheaters. Have you ever seen their walls are specially designed? Why do we design that? We
Yeah.
design that to absorb the noises and reflect the useful sound so that it can interfere constructively.
Makes sense. Makes sense.
Designed to give you constructive interference at where audience is seated, or I should say attend. Okay, audience are seated. A few lecture halls are so well designed that the lecturer doesn't even need to have a microphone. Whatever they say, every person sitting in the lecture hall, they're able to hear it, because before we actually design the lecture hall, we first decide the acoustics of that hall. That means we decide special positions where constructive interference will take place. That's where we actually keep the seats for the attendees. See, we can't actually put chairs or seats anywhere in a lecture hall. They also have to be specifically designed by a sound engineer so that the sound quality is the best, so that we give the best experience to the people who are attending. I'm going to show you what is a path difference. Path difference. Okay, this is going to be important. Path difference. I'm going to define this for you. It is the difference of distance traveled by two waves before they meet. Sorry, I should rephrase that. When they meet at a point. When they meet at a point. This is going to be a useful physical quantity for us, and why we will get to know it in some time. Imagine this is a source of a wave. This is a rigid surface. Okay, I'm going to show you a past paper question. This is a wave that travels to the rigid surface, gets reflected. Okay, this is 90 degrees. This is a point P. A wave comes from the source S, comes and reaches a point P, and another wave comes from the source S directly to the point P. They tell us that this length S to R is 5 centimeter, and from R to P is 12 centimeter. They ask us to find out what will be the path difference. The symbol for path difference is delta S. It's just the difference of distance traveled. Let's see. One wave that goes from S to R and then goes from R to P. This wave has traveled a total distance of 17 centimeter. So SRP, the total distance is 17 centimeter. Then if you want to find out the path difference, you will find out the distance traveled by one wave and then subtract the distance traveled by the other wave that is coming directly from S to P. How much will that be? That's very simple. You can use the Pythagoras theorem. If that's the hypotenuse, the angle, the length in front of a 90-degree angle is the hypotenuse. H square equals to P square plus the B square. P is 12, B is 5. You square them and then you take the square root. You get H to be equal to 13 centimeter. So this tells us that this H is 13 centimeter. So the wave that's coming directly from S to P, that will travel 13 centimeters when it reaches point P. So SP, the length SP is going to be 13 centimeter. You subtract 17 and 13, you get 4 centimeter. So this tells us that when the waves meet at point P, there is a path difference between them, and that's 4 centimeter. One of the wave has traveled a longer distance as compared to the other one. Do you understand what is a path difference? Just the difference of length.
Sir, is it always in like a triangle shape?
No, not always. Not always. If they are not, if the shape is not triangle, it can be, I'll give you another example over here. Okay, that'll clear things out. Let's say that's the source S1 and that's the source S2. Let's say they are both meeting at a point P. This S1, it will be given in questions. Let's say if that's 12 centimeter and this is given like 20 centimeters. So in this case, when the waves meet at a point P, they will have a path difference that will be equal to S2P minus S1P. S2P means length coming from S2 to P, and S1P means length coming from S1 till P. So the path difference in this case is going to be 20 minus the 12. That gives you a delta S. Path difference is delta S to be equal to 8 centimeter. That's an example 2. Here it was right angle triangle, so that examiner could create this mathematical confusion here, how to find out this H. It's not always going to be a right angle triangle. Okay.
All right.
All right. I hope you understand what is a path difference. I will tell you why I am discussing path difference for you. Okay. From this diagram, I'm just going to copy some stuff and paste it at the bottom because I'm going to make a lot of marks on this diagram and it's going to become confusing. Okay. All right. Now I am going to show you the path difference between points A, B, C, and D. Path difference for constructive interference points. Constructive interference points. Let's say one, I'm going to talk about the point A. Now, at point A, delta S will be equal to S2A minus S1A. From S2 to A, you can see how many wavelengths have been traveled. 1, 2, and 3. From S2 to A, the distance that has been traveled is 3 times the wavelength. And for S1 till A, the distance that is traveled is going to be 2 times the wavelength. So the path difference in this case is going to be equal to 1 wavelength. Why am I calculating path difference? You'll get to know that in a few minutes. Okay, but first learn how to find out the path differences. For point B.
Sir, could you explain point A again?
Okay, we are going to see what is the distance from S2 to point A. And then what is the distance from S1 to point A? We express that distance in terms of wavelengths. Can you see I have indicated with the blue arrows, double-headed arrows, the length from S2 to A, it is going to be 3 times the wavelength. Do you see that?
Yeah, I can see 3 wavelengths.
Okay. Similarly, for S1 till point A, you can see 2 wavelengths. That is why S1A is written as 2 lambda. So the path difference for point A comes out to be 1 lambda.
Okay, I got it.
So for point B, S2B minus S1B. For point B, we can see that the wavelengths that are coming from S2, the waves that are coming from S2, they are going to travel a total wavelength of 3 lambda. Similarly, for S1 to B, now the wavelengths are going to be 3 wavelengths in this case. So for delta S, path difference to be from S2 to B, that was 3 lambda. From S1 to B, that was also 3 lambda. So the path difference comes out to be 0 lambda. Do you know how I
Okay,
calculated
so
the
we
path difference?
basically use path difference to figure out which type of interference it is.
Yes, we are going to use that. See, I will show you how or why there is constructive interference.
Okay, okay.
For point C, we can see that for point C, the distance from S2 to C is going to be 2 wavelengths, and the distance from S1 to C is going to be 3 wavelengths, right? So the path difference in case of C, delta S, is going to be equal to S1C minus S2C. Why have I written S1C first here? Just so that I can write the bigger value first. 3 lambda minus the 2 lambda, that gives me 1 lambda as the path difference. I can safely say that in case of part D as well, point D, the path difference is also going to be an integer multiple of a wavelength. For point D, you can see the two troughs are meeting. So for point D, the gap from S2 is going to be 2.5, and the gap from S1 to B to point D, that is also going to be 2.5 wavelength. 2.5 minus 2.5, that gives you a path difference of 0 lambda. So as a conclusion of all these calculations, we can say whenever a path difference,
Sir, what's a delta S?
delta S is the symbol for path difference. Symbol for
Okay.
path difference. Whenever a path difference delta S is equal to whole number multiple of wavelength, constructive interference takes place. I'm going to make a formula using all this result. Delta S equals to n lambda, where n is equal to 0, 1, 2, 3, and it can have integer values, whole number multiples. So this formula here is going to be a necessary condition for the path difference. This delta S will be a necessary condition for path difference if there is supposed to be constructive interference. I'll show you what happens in case of destructive, but are you with me so far?
Yes.
Okay. Now, I'm going to show you sample calculation for destructive interference points. Okay. Path difference for destructive interference points. That means X, Y, and Z. I will show you only two, and that is going to get applied to all the points where destructive interference will take place. Okay, so I will show you the working for point X first. For point X, delta S is going to be equal to, let's see, where is point X? This is where the point X is. Can you see that it's going to be a total of 3 wavelengths from S2, and it's going to be 1.5 wavelength from S1. Are you with me?
Yes.
From S2, it's going to be 3 wavelengths away, and from S1, it's going to be 1.5 wavelength away. So I
Yep.
can write as S2x minus S1x is going to be 3 lambda from S2, is going to be 1.5 lambda from S1. So the path difference in this case comes out to be 1.5 wavelengths. That means if the path difference is 1.5 or simply 0.5 or 2.5 or 3.5 or 4.5 times the wavelength, there's going to be destructive interference. For 2, I'm going to show you for the point Y. Point Y is going to be delta S equals to S2Y minus S1Y. Let's see what is S2Y. Y is this little point over here. This point is 2.5 wavelength away from S2 and only 2 wavelengths away from S1. So S2Y will be 2.5 lambda and S1Y was 1 lambda. That gives me a path difference to be equal to 0.5 wavelength. So this tells us that if the path difference is half integer multiple of a wavelength, half integer, that means 0.5, 1.5, 2.5, 3.5. So I'm going to write that down as a rule here. If the path difference is equal to half integer multiple of wavelength, destructive interference takes place. I'm going to write down a mathematical formula for that. Delta S is equal to 2n plus 1 into lambda by 2, where n is equal to 0, 1, 2, 3, 4, and so on. If you place a 0 in place of n here, 0 times 2 becomes 0, plus 1 will be 1, 1 multiplied by lambda by 2, that gives you half a wavelength. So for all the values of delta S where it is equal to 0.5 lambda or 1.5 lambda or 2.5 lambda or 3.5 lambda, that's where the destructive interferences are taking place. So instead of writing all these values, we constructed an equation and we just keep changing n, and n is an integer. If you place 1 in place of n, that will be 2 times 1 will be 2 plus 1 will be 3. 3 times the lambda divided by 2, that's going to give you the next value, that's 1.5 wavelength. So for the next value, if you place 2 in place of n, that's going to be 2 times 2 is 4. 4 plus 1 is 5. 5 times the lambda divided by 2, that gives you 2.5 wavelength. So in case of destructive interference, the path difference is always going to be half an integer multiple. Okay, half integer multiple of wavelength. So if you have to check if there is constructive interference or not, or destructive interference or not, we are supposed to use these two equations. Are you with me so far? In physics or in mathematics, we prefer to use whole numbers in our formulas instead of actually making them half or using using decimal places. What we did was we designed an equation in such a way that even if we place a whole number in place of n inside the equation, the overall answer is going to be half of an integer. Okay, this equation has been designed in such a way that instead of n, whenever we place even a whole number value, the answer is going to be half, 1.5, and 2.5. So let's say when n is equal to 0, delta S will be equal to 2 times of 0 plus 1 and then lambda by 2. This gives you a path difference of 0.5 lambda. When n is equal to 1, even if n is 1, which is a whole number, when you place it in this formula, it gives you 1.5 wavelength. Do you see? This formula has been mathematically designed to give you half of an integer value. Do you get that?
I get that, sir, but in destructive interference, our values aren't in whole numbers, right? The length
Yes,
of the wavelength.
yes. That is why,
So
no,
how are we,
no, the path difference is supposed to be half of an integer. But in the formula, no matter what value you are placing, that can be a whole number as well. See, in the previous formula, n was also whole numbers. That formula was designed to give you a whole number multiple of wavelengths. That way it wasn't very complicated. But in this case, the formula is designed in such a way that if you place in whole numbers, it gives you half integers for the path difference. Okay.
okay,
What's troubling you? You can tell me.
I can't word it. Sir, we discussed that in destructive interference, the path difference is usually not a whole number, right?
Yes.
So you've got 3 and then like 1.5. How are we going to put the non-whole number in this formula?
We are not going to put a non-whole number. That's what I'm telling you, that this formula only works for whole numbers to give you half integer non-whole number path differences. That's the beauty of this equation. The path difference is supposed to be half of an integer. This n has nothing to do with the path difference. This n is just a number that you can substitute in the formula that will give you half integers.
Sir, could you explain this formula with an example?
This, okay, I'll show you an example. Let's say, okay, let's use the same example that we discussed earlier. The wave was reflecting from it and coming back down to a point P. This angle was a 90-degree. This was 5 centimeter. This was 12 centimeter. And a wave was coming directly from S to P in a straight line. Of course, that's not a good um, diagram. Okay. The two waves, one is the blue one and the other one is the red. They meet at a point P. You remember we calculated the path difference to be 4 centimeter. Okay. This was 13. If I tell you
Yeah,
that
yeah.
the wavelength was 2 centimeter, if the wavelength is 2 centimeter, do you remember? Can you tell me if there will be a constructive interference at P or destructive? If the given wavelength is 2 and the path difference is 4, you just divide this path difference with the wavelength. That will give you delta S to be equal to 2 times of wavelength. This 2 is the wavelength. Simply divide the path difference with the wavelength. That will tell you that the path difference is 2 times the wavelength. So see, wavelength has a whole number being multiplied with it. This is going to be your proof that constructive interference is taking place. If instead
Okay.
of this, let's use the next example that we discussed. This one, I will copy it from here. And paste it over here. Now, you remember the path difference was equal to 8 centimeter. Okay.
Yep.
So if it, okay, how about I change it a little so that we can see destructive interference as well. Okay, let's say the path difference was, here it was 12 and here it was 22. Okay, so now the path difference is going to be 22 minus the 12. That is going to be what, 10 centimeter. What if I tell you that the wavelength in this case was 4 centimeter? So inside 10, you can see there will be 2.5 of a wavelength. 10 divided by 4 is going to give you 2.5 wavelengths. See, the wavelength has half an integer being multiplied with it. So that means delta S is going to be, in this case, the second formula that we discussed. So there's going to be a destructive interference taking place here. Destructive interference. See, destructive interference takes place whenever the path difference is 1.5 of a wavelength or 2.5 or 3.5. That doesn't mean that in this formula, the number that you are substituting, that also has to be half a wavelength. No, the number that you are putting in the formula absolutely has to be whole numbers, because that's how this formula is designed to give you destructive interference. That means give you half a wavelength intervals by using whole numbers as input to the equation. Do you understand that? These are just input values. They don't have, they're not supposed to be half integers. Half integer has to be the final answer of the equation.
So what do you mean by input values?
Let's say I have an equation y equal to mx plus c. Have you done this in mathematics, that whenever you want to plot a graph, you will always have to assume a few values of x? That's usually
Yeah.
-2, -1, 0, and then that's 1, and then that's 2. So these are called the input value to the equation. You input them to find out y. Y can have any value. These are called the input values जो आपने खुद select की हैं. Similarly, for this equation to work, for this equation to give you different path, difference of destructive interferences, the input values are n equal to 0, n equal to 1, n equals to 2, n equals to 3. Do you get it?
Yeah, it's starting to clear up.
Okay.
All right.
All right. I'm just going to tell you one last thing for today. All this discussion that we have done, the two formulas that we have studied, necessary, absolute necessary condition, the two formulas that we have learned, they will only apply if, only apply, only applied when the two sources are in phase with each other. What does that even mean? What does in phase mean? First of all, do you register what I'm saying? The two formulas that we have learned, they will be applied only if the sources are in phase. Examiner will tell you if they are in phase or not. In phase means they are vibrating together. Same situation. What does that even mean? When one wave is creating a crest, the other one at that same instant should also be creating a crest. If one source is creating a trough, the other one should also be creating a trough. That is why you see the first line that I have drawn with S1 is a bold line. That means it is creating a crest first. Similarly, for S2, I have also drawn a bold line. That means S2 is also creating a crest first. So this way, they are both vibrating parallel with each other. When one source moves upwards, the other one is also moving upwards. When one source moves downwards, the other one is also moving downwards. That way, they are creating two waves which are in phase with each other, creating crests and troughs together. Okay?
Okay, okay. Yeah, I got it.
All right. So I am going to tell you one more thing here, but basically it's the same thing. In case of in case if their sources are 180 out of phase, what's going to happen?
In case of what?
In case of the two sources vibrate 180 out of phase, I'm going to write down
Oh.
this as a note and then we'll discuss it in the next class. If the two sources vibrate 180 out of phase, the formulas get interchanged. That means when one source S1 and S2 they are vibrating, S1 is creating a crest, but at the same instance S2 is creating a trough. That means they are moving exactly opposite to each other. That means when S1 moves upwards, S2 is moving downwards. So in such a case, the formulas for constructive interference and destructive interference, they will get interchanged. Okay. How would that work? We'll discuss that in the next class, but do you understand what I just said here?
I got it.
Okay.
Sir, regarding our next class, there was supposed to be was it Tuesday? Was it Monday? Either way, like one day we had to start our class, right? You said you'd reschedule.